Hi, my name is Rogelio Junior Macias. I will present the following work entitled Pore Size Effect on Corrosion Resistant on Highly Porous Titanium 6 Aluminum for Vanadium and 25 Tantalum Composites. Currently, biomaterials require specific biological and mechanical characteristics for their use as a medical implant material. One of the most commonly used materials as a biomaterial is titanium 6 aluminum for vanadium. This alloy has good properties such as low density, good corrosion resistance, and high rigidity. However, one of the problems is that it has a high Young modulus of 110 gigapascals. This modulus is significantly different compared to that of human bone, 10 to 28 gigapascals. This difference prevents optimal coupling between the implant and the bone. One of the options to reduce the modulus values is the materials is by modifying their structure. The addition of porous has proven to be a good option since in addition to reduce the Young's modulus, this porosity favors the anchoring of tissue adjacent to the medical implant. A methodology. In order to manufacture porous materials, titanium-64 and tantalum powders and porosity-forming particles such as ammonium bicarbonate salt are used. The salt is used in two different sizes, 100 to 200 micrometers and 300 to 400 micrometers, in order to evaluate the effect of pore size on corrosion resistance. In addition, the base of the matrix is a mixture of titanium-64 and 25% tantalum particles. This ratio is proposed because it has been shown to have the best mechanical properties and favors obtaining the beta phase of titanium. The preparation method was mixing the powders with the weight ratio between titanium and tantalum. In addition, these powders were mixed with a quantity of 40% of volume of ammonium bicarbonate particles of both sizes. Subsequently, this mixture was poured into a cylindrical steel mold to compact it with a pressure of 500 megapascals. The samples obtained were heated in an oven with a controlled argon atmosphere. A thermical cycle was used to eliminate the salt particles, and then the final sintering temperature was required at 1260 degrees centigrade to consolidate the material. The microstructure was observed by scanning microscopy after the sintering process. They were then taken to a microtomography. This process is used to obtain slices image of the length and width of the samples. Later, these images are processed in a software to obtain a three-dimensional image and to be able to manipulate the complete and in a non-destructive way to evaluate same properties. The corrosion tests were carried out in a standard 3-electrode cell with reference to a calumen saturated electrode, and the electrolyte was hang solution at room temperature. The solution is a fluid that simulates body fluids. The result: first, microstructural information was obtained by scanning microtomograph. It can be observed that the titanium samples with tantalum presents a biphasic microstructure, alpha and beta, where alpha is the darkness phase and beta is the lightness zone. In addition, it can be observed that the tantalum particles did not dissolve it completely. Also, the large pores obtained by the use of bicarbonate salts can be observed. Finally, it is observed that the martensitic phase is formed in the form of irregular needles. The microtomography behavior. Using the microtomography technique, the quantity and size of the pores obtained can be evaluated. The two-dimensional tomography shows the difference between the different pores generated by the size of the pores used. In addition, small unsolved tantalum particles were detected. Once the tomography images were processed, a three-dimensional representations of the evaluated samples could be obtained. The, the difference in the size of the pores obtained is clearly observed, and the software also showed that the pores are almost entirely interconnected, indicated by the blue color in the 3D image. The table 1 lists the pore fractions with a large difference between the samples without pores and the samples with pores. Likewise, the samples with porosity have a similar pore volume, but the pore size represents a difference of 3 times the size between the sample with small pores and the one with large pores. The presence of large pores in both samples favors the passage of fluid, which is essential for good implant coupling in the human body. It has been shown that the optimal pore size is approximately between 150 and 250 micrometers. The corrosion results showed that the E-core tends towards more positive values with the presence of large pores, and the E-core of the porous samples is lower compared to the reference sample without additional pores. These results indicate that pores and interconnectivity have a significant effect on corrosion resistance due to the exposed active area. The pores cause the sample to be attacked from the outside in, and then the activated area will increase the corrosion rate. At the same time, these large pores favors the obtaining of a denser oxide barrier and therefore a lower susceptibility to corrosion is presented. In conclusion, a more electropositive behavior will be observed as the pore size increases. Furthermore, the anodic current density showed a slow increase at higher over voltages, which could be associated with the formation of an oxide film. This reduced the susceptibility to corrosion due to a better distribution of the corrosive liquid due to the connectivity of the pores.